Good morning, class.
Good morning, sir.
Kindly inform your colleagues to join so that they are not behind. I'm about starting the class, and do we have a West Coast student here? Do you have West Coast students here? All right, so please mute yourself so that you. All right, please I'm sure you can all see my screen. So this course is basic general chemistry or general chemistry, and it deals with the inorganic aspects of chemistry, the fundamental principles of chemistry. And so we're going to look at some aspects as an introductory concepts to subsequent chemistry courses that you register and do. So I'm sure we've all heard of the atom, all heard of atom. We've all heard of the word matter. And just to revise our previous knowledge in these areas, we are aware that matter is anything that has mass and occupies space. If you are asked to define matter, it is anything that has mass and occupies space. And so when you look around you, wherever you are now, the environment you are now, you can see a number of items that are classified as what? Matter. Because Those items that are found in your environment, your surroundings, have mass or weight, and they as well occupy space. You can look around and talk about tables around you, chairs, bowls, stones, pencil, bag. In fact, you yourself as a human being, you have mass and you are occupying space. And so you are as also an example of what? Matter. Now, matter exists in different forms or states, and we are aware of the three characteristic forms of matter. Of course, there's been the fourth characteristic or state, which has also been discovered. We are aware of the solid state or the solid matter, the liquid state or the liquid matter, the gas state, and recently what we call the plasma state or the plasma matter. And these states of matter have certain descriptions. They have certain descriptions. The solid state has a fixed and definite shape. So any solid object that you find around you, its shape is fixed. It's fixed. If you have maybe you are holding your phone, your mobile phone, which is solid state matter, wherever environment that you take your phone, the shape of the phone remains the same. It does not change to a different thing. So that is solid matter. And for liquid matter, they have a fixed volume, but then the shape of the liquid matter is not fixed. In fact, the shape of a liquid matter is dependent on the container in which it is kept. So if you take water as an example of a liquid matter, if you put water in a rectangular container, the water will take the shape of the rectangular container. If you put the water in a circular container, it will take the shape of that circular, container. So the shape of liquid matter is not fixed. It's not fixed. It changes and it fits the shape of its container. Although the volume remain fixed. The volume remain fixed. Now, gas as a matter has neither fixed volume nor fixed shape. You don't have fixed volume nor fixed shape. So that is the characteristic description of the gas matter. Now, the recently identified fourth state, which you call the plasma, is like a mixture of the liquid and then the gaseous matter. Okay, has properties and characteristics of the liquid and the gaseous matter. So know what matter is, know the states of matter, know the description of the states of matter. Now, a little bit history. Somewhere 500 BC, there was this Greek thinker called Democritus. Now, this man, without performing any scientific research, without performing any scientific experiment, believed and concluded that matter, as we know, was made up of tiny, tiny particles which could not be seen with our naked eye. He then again said that these tiny, tiny particles that is made up of, that matter is made up of, could as well not be divided into smaller bits or smaller particles. So these tiny, tiny particles that constitute matter, Democritus, this Greek thinker, referred to them as atomos. Atomos. And atomos is a Greek word meaning atoms. Meaning atoms. So his conclusion of matter is that matter is not continuous. Matter is made up of particles. These particles are very, very tiny. And these particles, he referred to them as what? Atomos, meaning atoms. Now, this idea Democritus put across was not backed by any scientific experiment or research. He just thought, he just believed, he just imagined that this is how matter is made up of. And then it became an information for use for a period. Until later, we have some scientists who then decided to perform experiments to either confirm or disprove this scientific, information put out there by Democritus. And so we have the likes of John Darton, J.J. Thomson, Rutherford, and Bohr, who came out with different scientific experiments to give us more information about the composition of matter and atom as such. We'll be looking at some of these scientific postulates very soon. But quickly, let's look at some few evidence which supports the particulate nature of matter. Let's look at some few evidence, okay, that is in support that matter is made up of what? Particles. Now, if you are in your house and you fetch water into a cup or a bucket, and then you drop in the bucket of water or cup a dye, D-Y-E, and a particular common example of a dye could be the pen ink, okay, the ink in the pen. It could also be what we call blue. After washing white, clothes, we have some kind of powdered blue matter, which we normally spread it in water before we rinse our white clothes. We call it blue. Gentian violet. Normally, when somebody gets some kind of slight cut, you normally want to cover the surface of the cut or the bruise with what? Gentian violet. Now, these are all examples of what? Dyes, types of dyes. And we are saying that when these dyes are dropped in a cup or a bucket of water, you realize that the point of dropping them, with time, the entire water turns and changes color to the color of the dye. That tells you that that dye, which is an example of matter, is made up of particles. Other than that, if that dye was not made up of particles, after dropping it at one point in the water of bucket, in the bucket of water or cup of water, it would have stayed at that point, or it would have moved together to other points without spreading. And for the fact that it spreads and then the whole water changes color to the color of the dye, then that confirms that indeed matter is made up of particles. The next evidence to back this statement is the spread of perfume. Now, when we going out after dressing up, we apply some perfume, some body perfumes. Why? Because we want to smell good. Why are we able to smell good when we apply perfumes? It's because the perfume that we have applied, whether in a liquid or gas form or whatever form, is made up of particles. So even though you have spray on your dress or your body, it does not stick to your body. It doesn't stick to your clothes. But then it begins to spread in the environment in which you are or you walk. Okay, so that a passerby, somebody passing by or somebody close to you will smell that nice flavor of perfume. This is also an example to buttress or support the fact that matter is made up of what? Particles. Again, you are able to tell that there's a rotten substance in an environment or in an area by way of smell. So let's say there's a rotten egg or there's a dead animal in a locality, in an environment. How you are able to smell the bad odor from the rotten egg or the dead animal also tells you that matter is made up of particles. That smell is able to get to you because whatever dead body or rotten egg, which is a form of matter, okay, the particles then spread. And that's why you're able to smell, to be able to tell. Another example is diffusion. Diffusion. Diffusion also confirms that matter is made up of particles. If someone is cooking and you are not in the kitchen, but you are in the hall or you are even at the porch, and from the kitchen you smell the aroma of the soup or the aroma of the stew, this also confirms that matter is made up of particles, because the stew or the soup or whatever food you are preparing is matter. It's something that occupies space and has mass. It's a form of matter. And so for somebody from afar from the kitchen to smell it, it means that that matter is in the form of particles and is able to spread by way of diffusion so that somebody can smell the nice aroma. The last evidence I want to point out in support of the particulate nature of matter is that when you have a cup of tea and you drop in salt, or you drop in sugar cubes, you realize that the salt or the sugar cubes, as soon as it's dropped into the water, it dissolves okay, there's dissolution such that the salt particles or the sugar particles get totally dissolved in the water so that you cannot see it. Again, because it has dissolved in the water, whether it's the salt or the sugar, if you subject that water to heat in the form of evaporation, when the water is leaving, you realize that all the water will leave, and then you see the salt or the sugar particles in the form of what? Crystal formation. We call crystallization. All these are evidence in support of the particulate nature of matter. So this all confirms democratic thinking or thought that matter is made up of particles. So now we'll be moving to the experimental designs that John Darton, Rutherford, J.J. Thomson, Bose, they came about, all in giving us a proper perspective of what? Matter, and of course, the atom, the structure of the atom, and then how the modern day structure of the atom is like. So we're looking at the atomic theories. The modern atomic theory states that all matter is composed of atoms. And these atoms are composed of protons, neutrons, and electrons. Each element has its own atomic number, which is equal to the number of protons in its nucleus. Of course, if we are talking about an atom, then its description is that it is the smallest particle of a chemical element that can exist on its own. It is the smallest particle of a chemical element that can exist on its own. So if you talk about sodium element, if you talk about oxygen as an element, if you talk about nitrogen as an element, they are all made up of their what? Atoms, particular atoms. So sodium element is made up of sodium atoms. Nitrogen element is made up of what? Nitrogen atoms. Oxygen element is made up of what? Oxygen atoms. Calcium element is made up of what? Calcium atoms. So that is the definition of an atom. The smallest particle of a chemical element that can exist on its own, or it is also the smallest constituent unit of matter that constitutes a chemical element. And we've talked about the state of matter, solid, liquid, gas, and then the recent one, which is plasmium. So let's look at the first postulate. Or the first person to put out an experimental finding about the atomic structure, the structure of the atom. And we're looking at John Darton, who in 1808 came out with a concept that atoms play a fundamental role in chemistry. And he was able to develop his theory. Okay. Now he came out with 5 postulates. But out of the 5 postulates, currently 3 of them are classified as what? Inadequacies, or they are no more accepted, because even though at his time we accepted those kind of theories, but modern day and further experiments had, in a way, disproved some of his postulates. So for that thing, because if I'm examining you in your exams, I can ask you, list the 5 postulates of John Darton. You should be able to list the 5. And then if I ask you which of the 5 postulates is no more in use, or is no more accepted, or has some kind of what inadequacies or limitations, you should be able to point out those ones. So the first postulate John Darton put out was that all matter is composed of tiny, indivisible particles called atoms. So I remember some years back when we were all in the primary school, when we are asked to define an atom, this word never missed out. And the word is indivisible, the smallest indivisible. But we all know that the atom can be divided. Current experiment tells us that the atom can be divided into protons, neutrons, and electrons. So on that basis, if we say that matter is composed of tiny, indivisible particles called atoms, that can never be accepted now, because that tiny particles called atoms are divisible, and they are divisible to get other particles called protons, neutrons, and electrons. In fact, as we speak right now, it is even evident that the protons, neutrons, and neutrons are not the smallest particles of an atom, and that they can also be further divided into what we call the leptons and quarks. So it means beyond the proton, neutrons, and electrons, they can also further be divided into leptons and quarks. This all confirms to the fact that you cannot define an atom as what? Indivisible. So that was the first postulate of that, in which currently is not accepted because of the inadequacies in there. Then the second point is that all atoms of a specific element are identical in mass, size, and other properties. However, atoms of different elements exhibit different properties and vary in mass and size. So this second point, what John Darton seems to establish is that if you are comparing, please hold on, give me a minute. Hello. Yes, boss. I'm having an online lecture. I'll get back to you pretty soon. Yes, I've seen your message. I'll get back to you. All right. So what John Darton seeks to establish in his second point is that if we take maybe sodium, it contains sodium atoms. If we take oxygen, it contains oxygen atoms. So yes, the atoms of sodium and then the atoms of oxygen definitely will have different size and mass. And that is true. But then he also made it a point that in a particular element, okay, the atoms there all have the same mass and size, and of course properties. And that is where there's a challenge, because if you take, let's say, oxygen as an element, we all know that the concept of isotopy makes it a point that oxygen has different isotopes. We have oxygen 15, 16, oxygen 17. If you talk about carbon, we have carbon 12, carbon 13, carbon 14. So though it is the same element carbon, but if you talk about carbon 14, carbon 13, and carbon 12, their masses are different. Carbon 12 has a mass of 12. Carbon 13 has a mass of 13. Carbon 14 has a mass of 14. How can you say that these three isotopes of carbon, which is the same element carbon, have the same mass? They don't have the same mass. And it's because of what? The concept of what? Isotopy. We will get to isotopes very soon. That isotopes are elements having the same atomic number, but different mass number. So it's the same element having the same atomic number, but different mass number. So if you say that all atoms of a specific element are identical in mass, size, that can never be accepted. So the concept of isotopy had come out to let us know hydrogen has 3 isotopes: proton, deuterium, tritium. We have chlorine 35, chlorine 37. We have copper 64, we have copper 65. Okay. We have bromine 80, or bromine 79, and bromine 81. So there are a number of elements which exist as what? Isotopes. And because they exist as isotopes, you don't expect them to have the same mass. And because they don't have the same mass, their properties also vary. So the second point, as stated by John Darton, is what is there. But then I have identified the inadequacies for you to see. Then the third one, the third postulate, says atoms can neither be created nor destroyed. Atoms can neither be created nor destroyed, or be divided into smaller particles. So if you take something like uranium as an element, John Darton is saying that you cannot destroy uranium, you cannot divide uranium into smaller particles. But we also know that due to the concept of radioactivity, where a number of the elements are classified as radioactive elements. And when we talk about radioactive elements, they are elements whose atomic nuclei are very, very unstable, and so they can disintegrate and form other elements. And in the course of the disintegration, they emit radiations and particles. So the concept of radioactivity, which is also the basis of what? The atomic bomb, okay, and other concepts, also confirms that it is not true, it is not entirely true that you cannot destroy some atoms. Some atoms can be destroyed, some atoms can be created, and that is because they are radioactive what? Element. So the atomic nuclei are unstable, some with unstable atomic nuclei which disintegrate, and they form other elements when there's the disintegration. And then in the course of the disintegration, they emit radiations and particles. So you could see the first 3 postulates currently, when he stated them, it was accepted those times, but currently there are a lot of inadequacies, and so we don't really accept those 3. The last 2 are still accepted and they are used. and that is atoms of different elements can combine in a fixed whole number ratios in order to form compounds. If one or two compounds are reacting to form a product, okay, they don't combine in fractions, they don't combine in decimals, they combine in whole numbers. Okay, 1 mole of what? Hydrogen will combine with, or let's say 2 moles of hydrogen will combine with 1 mole of oxygen to form 1 mole of water. So atoms of different elements do combine, and they do so in a fixed whole number ratios. And that is true, and it's still true now. Atoms can be rearranged, combined, or separated in a chemical reaction, and that is also true. Okay, so this new slide I have given you is just a summary of all the explanations I've given. The limitations of Dalton's atomic theory. It didn't account for subatomic particles, for saying that atoms are indivisible particles. We know that atoms can be further divided into subatomic particles, protons, neutrons, and even these protons, neutrons, and electrons can also be further divided into leptons and quarks. So Dalton could not account for the subatomic particles, which is a limitation. He also did not account for isotopes, because some elements are isotopes, and isotopes, elemental isotopes, have different mass and they have different properties. It could also not account for what we call the isobars. In that case, we're talking about what do you call it? Again, isotopes. Okay, there's a difference between isotopes and isobars. So he also couldn't account for that, because the masses of atoms of 2 different elements must differ. Okay, even though they are what? Referred to as what? Isobars. So elements need not to combine in simple whole number ratios to form compounds. Certain complex organic compounds do not feature simple ratios. And an example is sugar, that's sucrose. And then all those kind of explanations I've given. Now the merits, the positive of Dalton's theory is that it was able to account for the law of multiple proportion, the law of conservation of mass, and the law of constant proportion were not violated by Dalton's theory. And so the theory provides a basis to differentiate elements and compounds. Any question, please? Any question up to this point? Any question?
Okay, sir, please. I have a question.
Please go ahead.
Okay. So please, I was thinking that, you see, John Dalton's atomic theory, although then there was not advancement of technology, so we could not defy some of his postulates. But right now, checking the advancement of this world, we know that the first 3 of his postulates were inadequate. So therefore, we do not have to take it into consideration by learning it. So I wanted to ask if there's a reason why we are still holding on to that postulate, although it has been advanced though, but we are still holding on to it. Do you have a reason for still holding?
All right. So the point is that, scientific knowledge is transitioning, okay? And we keep on building on existing knowledge and improving on. And in the scientific world today, as we speak, somebody will just discover something, and then in just the following day, another person can also come out with a different discovery, which would even be totally different. Okay, so yes, we just need to know where we're coming from and where we got into.
Thank you, sir.
All right. So like I said, if you know the story of the um, most anti-malaria drugs, okay, you realize that the first that was extracted from a plant source, which is quinine, okay, quinine was used to manage malaria. And if you look at the quinine structure, it was used to manage malaria for some time. Then the parasite got resistance to it. When that happens, then the chemist went back and then they introduced the element chlorine onto the quinine structure. And we had chloroquine. Do you understand? Now the chloroquine became more effective than the quinine. Currently, as we speak right now, if you have malaria, I'm not sure any doctor will prescribe chloroquine for you. Okay? Because now the malaria parasite has developed resistance to it. But then out of the chloroquine, we have most of the anti-malaria drugs on the market. They just took the chloroquine structure and then they modify it just to make it potent again. So all that we are trying to learn is that we need to know where we're coming from in terms of certain knowledge, okay, so that we can appreciate the dynamics and then the trend of what scientific research. So even now, there are things that we are learning in the university that in the next decade to come, scientific research and findings will come and disprove some of them. That, oh, this thing that you were saying A, B, C, D, it is not that, it's not as it was. Okay. And that is the beauty of what scientific research and findings. So yes, we just have to introduce you to where we're coming from and where we got into. All right.
Thank you, sir. God bless you.
So still on the atomic theory, and I've already talked about some of these things. The word atom comes from the Greek word that means indivisible. Okay. You see, that is where the definition of atom was said to be indivisible. But today, we know the atom is divisible to get protons, neutrons, and electrons. So all atoms of all elements are composed of electrons, protons, and neutrons called subatomic particles. Now, the electron was discovered as a tiny subatomic particle with a negative charge. So all electrons are negatively charged, and it is usually represented with this symbol, the letter E with a dash on top. Then the next subatomic particle is the proton, which is a more massive, when you say massive, it has weight, though very small in size, it has weight. And these protons are positively charged, and then we normally represent them with the letter P. The neutron is about the same mass as the proton, but then the neutrons are not charged. They are electrically neutral. They are not positively or negatively charged. And we represent them with the letter small n. And these are the subatomic particles. So for the three basic subatomic particles, what I expect you to know is their name, proton, neutron, electron, their location in the atom. Okay, we will see the true picture of the structure of an atom. But then the atom has a centralized nucleus, which contains the protons and then the neutrons, with electrons revolving around it in what we call shells or orbits. Now, we said the protons are positively charged. The charge value is what? Plus 1.602 times 10 to the power minus 19, okay, in coulombs. The neutron is neutral, so it is not charged. That's 0. Then we said the electron is also negatively charged, okay, and that is of the same equivalent, as the protons. But then the difference is that the unit charge, this one's +1 and this one's -1. Know the masses. The proton is approximately 1. The neutron is approximately 1. The electrons is 1/1480, which is the same as 0.00055. And then their masses, relative atomic masses. So know this information. So that is that on the John Dalton's atomic theory. Let's go to J.J. Thomson experiment and what he also was able to come out with. Please let me find out. Do you all have the course model? You have the course model.
Yes, please.
Please.
Yes, please.
Yes, please.
Okay.
Yes,
Is it the hard copy or the soft copy?
The soft
The
copy.
soft copy.
Soft copy.
Soft copy. Okay. In fact, for
So
this
please, I don't
course,
have.
you don't have. Okay. So those who have, share it on our WhatsApp page. Okay. So that those who don't have will get it. And then there are 2 different models that can normally are used for this course. And there's one of them that I use in setting my questions. But then aside that, you can see that the slide that I am just using now is a summary of the slide. So please, I will also be sharing with you my lecture slides, which is more summarized, and it will help you a lot. I hope that's fine.
Okay, sir.
Yes, sir.
Please.
Thank you. Will be much appreciated.
All right.
God bless you.
Now, J.J. Thomson, who was an English physicist, developed what we call the cathode ray tube, and that was used in his experiment. And his interest was to investigate the electrical charges, okay, that could be produced in low pressure gases. And the information there talks about how the cathode ray tube is composed of, the various compartments, and then what the tube contains. What is important is that during his experiment, a visible beam called a cathode ray appeared between the 2 metal plates. Oh, there's a background noise.
But I said,
Please, Amma, mute yourself, please.
So this beam, which we called the cathode ray, was deflected towards the positive charge and away from the negative charge. What does it mean? You see, if a beam is charged and then it is deflected to a positive center, it means that the beam is negatively charged. And if the beam is charged and is deflected away from a negative charge, it means that the beam is negatively charged. In chemistry, positive will reflect, negative will reflect each other, but a positive and a negative will attract. Okay. So when there was a deflection to a positive charge, it means that the beam that was being deflected itself is a negatively charged, particle. Okay. So J.J. Thomson was able to calculate the charge to mass ratio of these particles, and the results of his measurement indicated that these particles were much lighter than the atoms. Okay, and those cathode ray particles is what we now call them the electrons. So if you take an atom and you said the atom has a particle which is negatively charged, then it is the electrons. And it was these electrons that were deflected towards the positive center. So J.J. Thomson is attributed to be the person who discovered the electrons. So if in an exams I ask you a question as to who discovered the electron, then it is J.J. Thomson. It is J.J. Thomson. And this is just a pictorial view of the cathode ray tube. When you have time and when I share the slide with you, you can look at it and then know the various compartments and components and then how it operates. So after Thomson came Rutherford, and Rutherford came to also discover the protons. Okay, he came to discover the protons, and his experiment was that he used a beam of high-speed, positively charged alpha particles, okay, which were being produced by radioactive decay of radium. And you know, for an alpha particle, which consists of 2 protons and 2 neutrons, he was able to establish that there is a particle in an atom which is positively charged, and that particle he referred to as what? The protons. The protons. And that is the pictorial view of Rutherford's experiment. Rutherford's experiment. He made these conclusions, and one is that the volume occupied by an atom must consist of a large amount of empty space. A small, relatively heavy, positively charged body, that is the nucleus, must be at the center of each atom. So Rutherford gave us a pictorial view that if you take the whole body of an atom, there's a small portion called the nucleus, which is at the center. And that is where the mass of the atom is concentrated. Because in the nucleus, we have the proton. In the nucleus, we have the neutron. And these two are the most heaviest particles of an atom. Then there is a large space, okay, which is occupied by electrons moving around or orbits. So he gave this pictorial view about the structure of the atom. Yes, so this is a pictorial view that there is the central portion here where we have the neutrons and then the protons. And the two of them are in the nucleus of an atom. Then the bigger space of an atom, okay, contains the electrons. Contains the electrons. Sorry, let me type is atomic theory. All right. So all atoms of hydrogen have one and only one proton in the nucleus. All atoms of iron have 26 protons in the nucleus. So this number of protons is so important to the identity of an atom, and that is called the atomic number. So all that we are saying and the deduction we are making from Rutherford's experiment was that if you take the periodic table, all the elements there, they are unique in their own way. And the reason is that they have different number of protons. And this number of protons is what gives the identity of an atom. So if you take sodium element, it contains 11 protons, and that gives sodium its identity. If you take calcium, it contains 20 protons, and that gives calcium its identity. So the number of protons in any atom, in any element, corresponds to its atomic number. And this atomic number is what expresses the identity of an atom. Or element. All right, so we move on. They just the introductory aspect that I've given you about the atom, the structure of the atom. But before even I come to the slide you are seeing, let me also touch briefly on some aspect of Bohr's model of the atom. Is kind of a bit more refined. Okay, so it was Bohr who makes it known that even though previously we say that the structure of the atom consists of a centralized nucleus which contains protons and neutrons, and then a stream of electrons revolving around the nucleus in orbits or shells. Now, Bohr then came and said, no, the location in an atom where you can find an electron are not just shells, they are called orbitals. So he came out with the orbital theory, and then he said that we have different types of orbital, the s orbital, the p orbital, the d orbital, and for each of the orbitals, the total number of electrons it can accommodate. Previous knowledge, when we were using the shells, we see that the K shell, the first shell is K shell, which can take a maximum of 2 electrons. Now the L shell, M shell, N shell, the subsequent shells can take a maximum of 8 electrons. Now Bohr was trying to say that, you see, if you take, let's say, 8 electrons in a particular shell, all these 8 electrons might not have the same energy. So under what circumstances can you put them in the same kind of shells? Let me give a typical illustration here. If you come to the university and you are reading a program, maybe BEd Science, know that that is one program that you are reading in the university. But the same first year, you have other people who will be reading other programs. Okay? And so all of you, though you are in the university and you are all in first year, but then there is some kind of differences. You are never the same. Those doing BEd Science are not the same as those doing BSc Chemistry, are not the same as those doing Biological Science, are not the same as those doing Lab Tech and the rest. Though you are all first years, there are some similarities, but then there are also some variations. So Bohr was trying to say that in putting atoms in the same environment, you consider their energy. So electrons of the same energy are found in the same environment. And that environment is what we call the orbital. And like I said, we have the s orbital, which can take a maximum of 2 electrons, the p orbital, which can take a maximum of 6 electrons, the d orbital, which can take a maximum of 10 electrons, and so on and so forth. Of course, with the s orbital, it is just 1. But when you take the p orbital, it is degenerate, meaning even within the p orbitals, we have the px, the py, and then the pz. And each degenerate orbital can take a maximum of 2. So if it is degenerated to 3, that means 2 times 3 making 6. the d orbital is degenerate into 5. We have d1, d2, d3, d4, d5, and each degenerate orbital can take a maximum of 2. So 2 times 5 then gives you the maximum of what? 10. And so for Ball, he described a region or a location where there's a high possibility of locating an electron as an orbital, and not a shell. And like I said, we have different types of what? Orbitals. The S orbital, the P orbital, the D orbital, the F orbital, and so on and so forth. And so that is just the addition of Bohr's model. And so when you're asked to write electronic configuration, usually we want you to use the Bohr's model. If you're asked to write the electronic configuration for sodium, you don't have to go the old system of writing 2, 8, 1, where the 2 is the number of electrons in the K shell, the 8 is the number of electrons in the L shell, and then the 1 is the number of electrons in the M shell. Rather, you go the Bohr's model where it becomes 1s2, 2s2, 2p6, and then 3s2 or 3s1. Yes. And that is the Bohr's model. I'm sure with time and other areas, we will look at this one again and more. Now, let's look at the laws of chemical combination. Basically, there are 3 laws, where we have the law of conservation of mass, the law of multiple proportion, and then the law of definite proportion, the law of constant proportion, and the law of definite, So we'll be looking at them and see how they vary from each other, and then how we can apply. So just look at what is on the screen, which talks about the law of conservation of mass, with an example there, and then a solution. I will take you through very soon, but look at it first. Let's give ourselves some few seconds to look at it first. All right, so the law of conservation of mass says that the mass of the product in a chemical reaction must be equal to the mass of the reactant. In simple terms, if you are combining 2 reactants, let's say reactant A with reactant B, and you are forming product C, okay, the mass of the product that you are formed, which is the C, should be equal to when you add the masses of reactant A and reactant B together. That is the simple understanding of the law of conservation of mass. Conserving mass means that I started with 10 grams, so I should end with what? 10 grams. The reaction has the reactant side and then the product side. So what I'm putting in are the reacting particles. If I know the mass, then at the product side, I should get the same mass. Then it means that mass has been conserved. There was no mass loss. Yeah, there's a hand up. Let me pick it, and then if there's a question. Yes, Augustine Akum.
Yeah, sir, please, can you go over about the loss again, since we cannot see the screen very clearly, because some of us, we are making some points. So please, I want you to just go over about this, about the loss again for us.
You can't see my screen.
We can see, but we cannot see it clearly.
Oh, how? Just a minute.
Okay, sir.
Is it better?
Yes, please. Now it's somehow better. Yes, please.
All right. So I was saying
Okay, sir.
that we are going to look at the laws of chemical combinations. Okay. You see, in chemistry, we always talk about chemical reactions. And in chemical reactions, what happens is that we combine some one or two things and then we form something out of it. Those that you are combining is what we call the reactants. And then what is coming out is the product. Okay. And one of the laws that governs this combination is the law of conservation of mass. When we say you are conserving something, it means you are protecting something. So we are saying that if initially the reacting particles, the two reactants that you are combining, they have some known mass, then after they combining to give you a product, the mass of the product should be the same as the mass of the individual reactants combined. Now the law is trying to say that despite chemical reactions or physical transformations, mass is always conserved. Okay, mass is always conserved. So the total mass of substances present after a chemical reaction should be the same as the total mass of substance before the reaction. Okay, so what it means is that the input mass should be the same as the output mass. Now there's an example there. I want you to look at it. I'll bring some of these questions in your quiz, so take note. A 0.455 gram sample of magnesium is allowed to burn in 2.315 gram of oxygen. So you see the two reactants that is combining, they are magnesium and oxygen, and they have their masses that they are combining with. The magnesium mass is 0.455 grams, and then the oxygen is 2.315 grams. So all we are saying is that if these two form one particular product, okay, then the product mass should be the mass of these two reactants combined. That is 2.315 gram plus 0.455. Whatever you get will be the mass of the product that you form, if that is the only product that you form. And of course, if the product forming is also not one, but then two, then when you add the mass of the two products, it should be the same as the mass of what? The reactant particles that were used in the reaction. So after the reaction, no magnesium remains, and the mass of unreacted oxygen is that. So what mass of magnesium oxide is produced? Okay, so the solution is here. I want you to have a look at it. So the mass of the oxygen that reacted is 2.315. Okay, so you subtract the mass that do not react, which is the 2.015. And then you get to know the mass of oxygen that reacted. So knowing the mass of oxygen that reacted, which is 0.300 gram, then that mass should be added to the mass of magnesium that reacted completely, 0.455. And the two will give you 0.755, which should be the mass of what? The magnesium what? Oxide. Assuming all the oxygen had reacted, then it means that the 2.315 gram should have been added to the 0.455 gram to give you the mass of what? The magnesium oxide that was formed. So I will share this slide with you, and then you'll get to know. So now there's a practice example, and I'm giving you Just some few minutes to try your hands on everybody, because I'm going to call you by name to tell us your answer. A 0.382 gram sample of magnesium is allowed to react with 2.652 gram of nitrogen gas. The sole product is magnesium nitride. The sole product is magnesium nitride. After the reaction, the mass of unreacted nitrogen is 2.505 gram. What mass of magnesium nitride is produced? Please, all of us, let's try our hands on this practice. And then when we are done, we check whether we are on the right path. So I'm giving you some minutes, take a pen and paper, and then try your hands on the practice question you can see on the screen. I know some of you are finished, but let's give some few seconds to others to also finish, and then I'll take your answers, okay? So those whose hands are up, yeah, let it be there, okay? Just keep your hand up there. Let me give some few seconds to some of your colleagues to also finish up, and then we'll look at it together. All right, so let me take the answers from students who have done it, and then they are ready with their answers. I can see Nana Marvelous hand up, Godfrey Jones, Rosina. Yes, so just unmute yourself and tell us the mass of the magnesium nitride produced. So Nana?
Yes. Please, should I give my answer?
Yes.
Okay, please, I had 0.529 grams.
0.529 grams. Okay, Godfrey, let me take yours.
0.529 grams.
Sir, 0.529 grams.
Okay. All right, Rosina, let me take yours.
And please, I had 0.529 grams.
All right. Is there any other person? Because the three of them are all giving us the same figure, 0.529 grams. Is there any person who had a different figure, a different answer? So it means if I give you a question under the law of conservation of mass, first I'll ask you, okay, state the law of conservation of mass. You state it. And then I will give this question there and I ask you to calculate it. I'm sure you can all do it and get your full marks. Yes, so the answer is 0.529 grams as indicated. Now let's look at the law of constant composition. I said there are three laws: the law of conservation of mass, the law of constant composition, the law of multiple proportion. So the second one is the law of definite composition. And this was proposed by Joseph Proust. And this law of definite composition is also the same as the law of constant composition. So wherever you see the law of definite composition, it is the same as the law of constant composition. What does this law state? It says that in a given chemical compound, if a given chemical compound contains its component element in a fixed ratio by mass and does not depend on its source and method of preparation. Okay, so if let's say you are preparing water, okay, and you know water is H2O. Now, however you came by the preparation of the water, it is immaterial. What is important is that the component of the water, the elemental component of the water, okay, will have 2 atoms of hydrogen and 1 atom of oxygen. Are you getting it? So there's no way water, somebody will say that, oh, water is H2O. And then in H2O, you have 1 atom of oxygen, 2 atoms of hydrogen, and another person will say that, oh, water is H4O2. Another person will say that, oh, water is H8O4. No. Water has a definite composition. Definite. It's constant. Anytime you talk about water, you see 2 hydrogen atoms and 1 oxygen atom. Nitrogen is what? NH3. Okay, the composition is constant. 1 atom of nitrogen and 3 atoms of hydrogen. Okay, so this law was supported by Dalton's atomic theory. And it does not account for isotopic mixtures. Still on the law of definite proportion. So a given chemical compound contains its component element in a fixed proportion by mass, regardless of the source or the method of preparation. Let's say you have a chocolate cake recipe that feeds 4 people, but you are going to a birthday party that will have 8 guests. Each ingredient will double, but then the proportion will stay the same. Okay, so the ingredients in terms of mass, you are going to weigh more. Do you understand? Just so you can feed the 8 people that are present. But then the particular cake, you know, the particular chocolate recipe will have the same composition. Okay, 11% hydrogen, and then so that of the water is what you can see on the screen. Okay, so for every water molecule, you have 2 atoms of hydrogen, 1 atom of oxygen. Okay, and it doesn't matter whether the water that you are producing is from underground water or is from seawater, is from rainwater. It's the same chemical composition that you see. So this is ethyl alcohol, ethanol. Okay, if you take alcohol, ethanol, its chemical composition is that there is 2 atoms of carbon, 6 atoms of hydrogen, and 1 atom of oxygen. So by way of percentage composition, the total carbon percentage is 52, hydrogen is 13, and then oxygen is 35. What it means is that alcohol that we know, however you produce the alcohol, whether by way of distillation from a palm fruit, whether it's by producing the alcohol from whatever source, from an ant or animal source, it doesn't matter. When you produce the alcohol finish, it will all have the same chemical composition. You will not say that, oh, this alcohol was produced from palm fruit, and so its chemical composition will differ from this alcohol, which is produced from what? An animal source or whatever. So that is what we mean by the law of definite proportion or constant proportion. The third law is the law of multiple proportion. Now, the law of multiple proportion is the third postulate of Dalton's atomic theory. In fact, it is a rule of stoichiometry that was proposed by Dalton. And that law says that when elements are forming compounds, when elements are combining to form compounds, the proportion of the elements in those chemical compounds can be expressed in small whole number ratios. Small whole number ratios. Okay. And this law was based on Dalton's observation of the reactions of atmospheric gases. So take note of that. So I expect you to be able to state the 3 laws of chemical combination. That is the law of conservation of mass, the law of constant composition, and the law of multiple proportion. And these are examples to buttress the law of what? Multiple proportion. I'll give you these slides so that you can try your hands on the examples that are there. Now, let's look at the example on the screen. Whenever you are reacting carbon and oxygen, you can form carbon monoxide or carbon dioxide. Carbon monoxide is CO and carbon dioxide is CO2. Now, in CO2, the ratio of the amount of oxygen compared to the amount of carbon is a fixed ratio of 1:2. A ratio of simple whole numbers. Okay. In carbon monoxide, the ratio is what? 1:1. The ratio is what? 1:1. So this one is still talking about the law of constant proportion. It's just an additional information. The law states that in any particular chemical compound, all samples of that compound will be made up of the same element in the same proportion or ratio. So water molecule is always made up of 2 hydrogen atoms and 1 oxygen atom, whether the water is from rainwater, seawater, however the water is produced, you are always going to get 2 moles of hydrogen atoms and 1 mole of what? Oxygen. That is the mole ratio. And that talks about what? Constant composition. The composition of a water molecule is always constant. That of ammonia is NH3. 1 mole of nitrogen, 3 moles of hydrogen. It's always constant. If you look at the relative masses of oxygen and hydrogen in water molecule, we see that 89% of the mass of water molecule is accounted by oxygen, and the remaining 11 is the mass of what? Hydrogen. Multiple proportions are also possible. For example, hydrogen and oxygen may combine in different proportions to form hydrogen peroxide rather than what? Water. So if you are comparing water and then hydrogen peroxide, then we are seeing the law of what? Multiple proportion, okay? Because in peroxide, the ratio of hydrogen to oxygen is 1:1, whilst that of the hydrogen to oxygen in water is what? 1:16, and that will be the same for the molecule of what? Hydrogen peroxide. So take note of that. There's some example here with solution, and then there's a practice question here, which you need to go through. After the lectures, I will share this with you on our HOSA page. That's the CHE107D page. And then please try your hands on this practice example. And then where you have a challenge, consult a colleague who understands to help you. Consult other materials to get further understanding. All right. Please, let's have a brief discussion. For now, I'm ending the class at this point, okay? I'm ending the class here. I wouldn't want to start a new. These are all solutions to the questions that have been given. You know, it's always good to practice, more. But then before we move on to another topic, I will end here. And let us, please, let me find out from the class. Can we have a meeting on Tuesdays at 7 p.m.? Just 1 hour.
No, sir. Because they have, I think we have gotten some information that Monday.
Proposed schedule. We have our class on Tuesday. At that time, at that same time.
On your timetable, you have a class on Tuesday.
Yes, please.
Yes, please.
Tuesday.
Can you pick a day in the week that you don't have a class?
Let's make it Thursday. Thursday will be okay.
Yeah,
Thursday. All right. So
Yes,
we all agreed on Thursday, 7 p.m.
Tonight.
Yes, please.
Yes. So right. Thursday, we will meet and continue from there. Okay?
Okay, sir.
Okay, sir.
All right, so please, we will end today. But like I said, however information I've given you today, you have to go back and revise, and then make sure that you understand the basis as we move on. On Thursday, we will meet and continue from there. Okay, and then I would as well, beyond the lecture slides that will be given to you in addition to the model, I'll be giving you what I call tutorial questions and then review questions. Now, when I give you those questions, please do well to go through them, okay? As an individual or with some of your center members, you can meet and then solve them. Some of the questions, I'll provide answers to it as a guide. And then when you are able to try your hands on all those things, then you will be okay with my quizzes and then end of semester exams, and you will pass and pass well. So I will end here, and then have a nice weekend and see you on Thursday. Bye for now.
Thank you. God bless you, sir.
Hello. Thank you, sir.
Other people are getting from
different campuses. They are just all the courses agree. Mm. Easy. He's still around. It's like they're now asking the question about thing on the it's, okay. No. Nuclear rotation in isotopes.
5 and 6, yeah, 5 parts each.
Yeah,
So,
5 parties
so now we are supposed to divide ourselves into two groups.
into two groups.
Yes, so we divide ourselves into two groups. Then under each of the units,
Mm.
we divide ourselves into another group again. In one group we take a sub-unit.
Yeah, another group.
Sub-units, so that we clear that one. Then the other group, they also divide themselves into sub-groups and now take the sub-units. So the way you were saying, so you said that the presentation dressing is going to count.
Hey,
Presentation, so you said if you dress decent.
and that will be next week.
Decent that is talking about, I'm sure you can
Shoe and coat
just
analysis.
condemn the sleepers.
Mm. But I think the physics and semi said they will do it face to face.
Another one. Mama doctor big na so wow. Don't come back to. Na so mama. Chemistry. So no almost 2 hours.